Hello and welcome back. So in this video, Lee, you're going to be implementing hash2D.
Right. As we saw in the last video, hash 1D is good as long as the numbers that we're doing are fairly sequential, don't repeat, and we don't need to do something like send in X and Y or X or the product of X and Y. It just can't handle that complexity. It's good for sequential numbers, but not things that are going to repeat. There's just too many duplicates that are spawned from it. So we're going to take this code and we're going to modify it so it can handle a little bit better. So we'll just duplicate the hash 1D, go ahead and paste it, turn this into hash 2D. Now, I still want to keep the concept of a seed, even if I do have individual X and Y positional information to feed in. I still would like to be able to vary the seed. So if for some reason I had the terrain and it was at patch 1.1, but I wanted to have a different number generated for different purposes, I could vary the seed and still get unique information with the same X and Y. So in this case, we're going to bring in a float X and a float Y. Now, we need to take this information and kind of massage it together with the seed. So we've got a unique number that we can get for instead of seed here. So what we're going to do is we're going to create another var, just call this n, and n is going to equal our seed plus our x multiplied by, not 8, multiplied by 73. And to that, we're going to add our y. We're going to multiply 179 to that. Again, these are just prime numbers. So you can modify those to get different results. So if I really wanted to, just to save time so I don't have to go through it, I can just say seed equals seed plus x times. So it'll do this whole equation. That way I don't have to go through the rest of it now. Because floats here, and I'm expecting integers, I will have to cast these to ints. And we'll address this issue shortly as well. So if I go ahead and build that, and I want to bring this up because I want to look at this number. We've got about 870,655 duplicates. So about 871,000 duplicates is what we're working with. So we're trying to beat that, or hit less duplicates, not more
Right, we're trying to
duplicates.
improve by having less duplicates.
Right. The other thing I'm going to do before I do that is I'm going to take our comment here, and I'm going to convert this to a region. And then down here in that region. Just so I can collapse it. It'll save me time scrolling up and down. There. That'll get rid of that. All right, so let's go ahead and we'll make another one of these. So duplicate that, paste it, comment out the one before it. Now here, I'm going to use the same. Let's see, if I go up here, I was seeding with the number 20, so just to keep consistency, I'm going to seed with the number 20.
And then change over from 1D to 2D.
What's that? Oh yeah, you're right. Good catch. I was already planning my next move, which was to go up here and change my count. So if I go ahead and run this, so with 400 iterations, we've got 0 duplicates. Good distribution, good mean, so we're doing good there. Now, what happens if we go with the full 1 million? So 1 million, still good distribution, good mean. Time is still good. We're better we're down to 761,000 as opposed to, what was it,
800 and some
861,000?
odd. Yeah.
Yeah, so we've, got 1,000 less duplicates, but still a substantial number, almost three-quarter or over three-quarters of our numbers are duplicates. So we're still not there. What can we do to fix that? Well, we know we can take in float information. So we're not getting float information yet, but we can still take it. Let's leverage that fact a little bit, and we'll make another method, and we'll modify these numbers a little bit to give us something that will give us less duplicates. So we're going to make a private static. This is going to return an int, and I'm going to call this fractional part. So what I have in mind is I want to take the fractional component of the float, pass that, so we'll pass a float into this, and then I want to take the fractional part out, and I want to return just the fractional part. So if x was like 10.25, I want to return 25 as an integer, as opposed to the 0.25. So that's what I want to do here. So I'm going to set this up as a double n, and the reason I'm setting this as a double as opposed to a float is for later, because we will be using this in other methods as well. So I'm going to create a var s is going to take and convert it to a toString. Now our floats can get fairly large, and if our floats switch over to scientific notation, that will break this method. So I'm going to format it with 9 decimal places. So because we are literally using a double, I can say use 9 decimal places and don't go to a scientific notation. Then I'm going to get the substring. So what I want to do is look for specifically the characters that are after the decimal place. So I'm going to say s index of, and I'm looking for the decimal place, the period. For those of you in other countries, you'll probably have to modify this code so it works with your regional settings. There's ways that you can do it inside of .NET. I just don't know them off the top of my head. Parentheses are just killing me today. You notice that? So I'm going to do a check that says if s equals string.empty. So basically, if for some reason we get s coming back with nothing in it, then s is going to equal the string 0. The reason why I want this is because I'm going to return our string that's been parsed as an integer. And if we send in an empty string to this method, it won't be happy. So this will just make sure that if the string is empty, we're going to tell it to be 0, which means the int parse method will just return 0 out of our integer. Now we can take this and we can come back up to our method here, and we can do some fun stuff with it. What I'm going to do is I'm going to create a new var. I'm going to call this UX, and in it I'm going to say take our integer of x, and then to that I want to add our fractional part of x, hit semicolon, go ahead and duplicate this. And this will be uy. So what we're doing is we're getting in a float. Right now we're passing in integers. So this won't do anything right off the bat because let's say we've got 10. So I pass in 10. This is taking the integer part of it, 10. The integer of 10 is 10. Then we pass in the fractional part of x, or try to get the fractional part of x. We pass in 10. 10 comes back as no fractional part, so it comes back as 0. So we're adding 0 to 10. So as long as we're passing in integers or anything without a fractional part, these will have no effect. So if I modify this code as well, so I know these are going to be integers, so I don't have to cast these anymore. So if I run this, we should see the same thing as we had before. It doesn't do anything. So 761,000. Where this does come in handy is if I were to send in floats instead. So if I were to say, floats. So because before we were sending in integers, but if I send in floats that have decimal components, we get a substantial drop in duplicates.
Very big drop.
So this fixes this part of it, but we still have that problem. We have to deal with what if for some reason we're not sending in floats. We literally are sending in integers, like our patch terrain. Our terrain patches are positioned at whole units based off of their spacing and their vertex count. So each one is 96 units away from the last one, exactly 96. So it's 96.0. We don't have any integer parts, so we would still incur that penalty that we have before. Well, the cool thing is we can take our fractional part, and when we're passing in information, we can go take x, multiply it by some fairly large double, which is why we're taking doubles in here. So where we were taking in with the integer and we're passing in integers, we're still, again, back to passing in integers. But now we're taking the integer part of it, and then we're passing in the fractional part of, a very small fraction of x because we're multiplying it by this number. So what we're going to get back is going to be some other number which we're going to add to ourselves. So if I take this and I run it again, we're better. We're down to 275,000. Not as good as if we're using real floats or doubles passing in, but still a lot better than 760,000.
Mm-hmm.
And we can add a couple more zeros. This starts yielding diminishing returns after a while, and to the point where it goes the other way. So trying to find the sweet spot where it works best is just some trial and error. So we're back to 750. Now we can also go through here.
Did you say 750?
Or 275.
Oh, okay.
I thought I said it wrong. But instead of the addition here, we can do multiplication. So now we're down to 14,000 as opposed to 275,000, which was down from 890,000, I think it was, when we were doing the product of X and Y, which was down from 960,000 or something like that when we were doing the summation of an X by Y. This, out of 1 million iterations, is a lot better. So this gets us a long way from where we were. Now, this is still doing a hash. We can also modify it as well, and we can do a different technique as opposed to using this type of hash, and that's something that we'll explore in the next video.
All right, fantastic. Well, with that, that is going to wrap up this video. Thanks a lot, everyone.